this extra electron is weakly bound, and it has a tremendous effect on the conductivity. Because what can happen, oh, I chose the wrong kind. Maybe I should have put in boron. Suppose you put in boron. Boron is from group 3. So it has 3 bonds like this. And it has an empty orbital, as it were, compared to silicon. So it can actually fit into the silicon lattice, but it's missing an electron here. So what can happen is that an electron from another silicon atom can jump into this hole and leaves behind a hole. And so you get what's called hole conduction. That is, the hole moves. The analogy is if you had a parking lot, and there's an empty space. If a car moves into that empty space from from a full space, the hole where the empty parking space is, that hole moves, and that's a kind of conduction. That's a conductivity. It's a moving charge. Actually, it moves oppositely to the way the electron moves this way, but the hole moves that way. So the hole acts kind of like a positive charge, and we call that p-type conduction for positive. As against this case, where you put in arsenic and it has an extra electron, and that electron is thermally excited. It's a negative charge, and we call it n-type conduction. So you have p and n-type conductors. This particular graph is a very early one. It was actually a paper in which the name here, I don't know if you can read it, is Bardeen. He won the Nobel Prize for this work, inventing the transistor, which is, of course, the basis of all our electronics these days. And what they noticed was that you could get, by adding, let's see if I can read that, 0.0013 atomic percent. That means it's really 0.000013 atoms per silicon atom, sort of like 1 in 100,000. But that's enough. That raises the conductivity by hundreds of thousands, because this is going from 0.01, 0.1, 1, 10, 100 to 1,000-fold conductivity by the addition of this 100,000th of a percent, 100,000 per impurities. And you increase it. Well, look how low that is in pure silicon. But you put in a small amount of this 1 per 100,000, you get 100,000 carriers. So what are they doing here? What are they changing? In this formula, what they're changing in the conductivity is the number of carriers. And this is what you're doing in the semiconductor industry. They're changing the number of carriers, which in silicon would be 0 practically at room temperature, be useless. So the first order thing is you're changing the number by putting in impurities, p or n-type impurities, and that raises the conductivity to a useful level. Then what you see as a function of temperature, well, you see first, you see how the conductivity goes up with temperature? Why that is because you're releasing the bound electron. This electron is sort of circling around the boron, let's say. It's circling around, the hole is circling around boron, it's going to attach to boron. But if you put enough energy, you can get the electron from the silicon to jump into the boron, but you have to give it a little kT to do that. So with a little kT, you can excite the holes to start moving. So that's what happens on the early part of that curve. Namely, if you look at the temperature is actually increasing this way. And you see that the conductivity goes up first, because what's happening is you're thermally exciting the electrons. You sometimes have a picture something like this. The boron is here. You're exciting a hole into the boron. Then the electron goes into the boron, and the hole starts moving. So that's thermally excited. But once they're up there, then the heat does you harm in a way, because then the lattice is moving, and those moving holes start to scatter. So the conductivity turns down. So that's the explanation of that curve. You see, on the one hand here, they're being thermally excited. The holes are being thermally excited. And then over here, the heat is getting where it's slowing the electrons down in their motion. Okay? But this makes silicon into a useful material. And the trick is, this is the kind of crazy stuff that they make in Silicon Valley. You see, there's all kinds of things. You have p-type substrates, you have n-type here, you have p-type there, you have n+ there, and you have all kinds of wires attached to these things to help the electrons tell them where to go from n to p and p to n and blah, blah, blah. And it's really complicated stuff, and that's what they do in Silicon Valley. It's complicated, so you don't have to know this, believe me. If you want to, you're welcome to it. But you can control the currents and make this into switches. You can make them into amplifiers. You can make them into oscillators. You can make them into storage units. Like the flash drives are made of stuff like this, where you have various N, which would be like arsenic and antimony regions, and somehow you have to chemically introduce them into this region and have a little gap in here and put this in here. It's a gigantic and expensive business, but somehow they're mass producing it so you can buy a computer for a few $100s. It's really amazing how they got that down. And these are extremely tiny wires that they have attached here. And you've seen pictures perhaps of the network of wires and to connect to these things. It's quite phenomenal. Now, the only other thing I wanted to point out to you, those things that have a lot of carriers in them, so where N is due to the fact that, like lithium, where every atom is giving up one electron to a conduction band, and so you have the order of 10 to the 23 per mole of electrons, then the story is a little different. See, here you have like a half-filled band, and the electrons can run freely around in that free energy levels within the band. Then what controls the conductivity, now N is pretty much constant, because that's just given by the thing. So in a metal, N equals on a metal, it's pretty hard to change N. It's somewhat doable. People have tried, where you try to suck the electrons out of a metal by putting some kind of a gate to pull them out, but it's very hard. So N is more or less a constant. The only thing you really have to work with is tau, which is the mean free time for scattering. And so you can play with that. And your options are, well, the resistivity, or that's the inverse of the conductivity. Impurities obviously hurt you, because the carriers, as they move along, bump into the impurities and they scatter, so that shortens the scattering time. The other thing is lattice vibrations. That is the temperature causing the lattice to jiggle, and that sort of slows down the passage of free carriers. And the other thing is surfaces, like if you have grain boundaries in a material. Where it isn't a single crystal. So if you make a material a nice single crystal, you can get rid of this. Temperature you pretty can't get rid of, you see, and that's unless you cool it down. If you cool it down enough, you can get rid of some of the resistance. And then you're left with impurities. And if you make the material extremely pure, like apparently they did here, you clean it up and get out all the other things other than, say, pure copper, you can make it very, very pure and make the resistance go almost to zero at zero temperature. So we speak of this part as the thermal resistance. We speak of this part as the impurity resistance, and also grain boundaries you have to get rid of. Now, the other phenomenon that I did want to mention just in passing is the remarkable phenomenon that what they discovered about, just about 100 years ago, 1911 or 10, was that some materials, when you cool them down, granted, the thermal vibrations go down and down, and the material passes current better and better, resistance goes down, but at certain temperatures, the resistance drops to zero, literally zero, which means that, in fact, if you started a current going in a loop, it would continue for thousands of years without a battery attached. And around 1986, some people discovered materials which would do this at a reasonably high temperature. This is in degrees Kelvin. You remember that liquid nitrogen is around here 77 Kelvin. So this material, if you put in liquid nitrogen, would have zero resistance. And that's, of course, a lot of excitement as a possibility of making material like transmission lines. It might be cheaper to make a transmission line from a power plant and have it inside, cooled by liquid nitrogen rather than suffer the losses of power in the resistive wires. Some of that promise has been carried through, and so there are some very useful high-temperature superconductors. Before this discovery in 1986, the lowest temperature, or the highest temperature, was around 20 Kelvin, around in here, was where some materials. But then they found this class of materials, the cuprates, copper oxides, with various rare earths in them, had this very high transition temperature. I think the temperature is now up to about 106 or so. It's about up here now. This slide being a little bit old. It comes from Wolfson, actually. So it's perhaps not the most optimal, but it's around 106, which is very, very good. But these materials, it turns out, are hard to work with. They're kind of brittle ceramics. Yes, Nathan? Yeah. Yes, the hope was that it could make faster computers. And also, the other thing, that's a very good point you raised, Nathan, the question of speed and computers. One of the things, since there's no resistance, there's no heat when the electricity flows through this. And one of the big problems with computers, if you pack all these circuits together, and each of them is doing its little thing, each one may not produce much heat. If you've got millions of them, you've got a lot of heat, and the whole damn thing may melt. So it's one of the real limitations of computers is just the heating that goes on. And it's a serious problem. If you design a computer, they actually have water flowing through the chips in these very dense big machines because they've got to get the heat out, or else the thing will melt. So and IBM, for one, actually when I was there was a whole project on trying to make a superconducting computer. It didn't quite work yet. Now this stuff, the cuprates, might be very hard stuff to work with because they are hard to deal with. It's hard to deposit them into very thin layers and connect to them, and there's a whole technology you need. And they're not thinking, I don't think, of making large-scale computers out of this stuff. But what they could do is make, for example, for MRI machines where you need a large magnetic field, you have to pass a lot of current to get a large magnetic field, Ørsted's current and magnet. There, it's not tiny, so you can maybe make real fat wires. And so for MRI machines, this is maybe a thing. And also for the large magnets they need in atom smashing machines like at CERN, this would be very good because you could not have heating, and you wouldn't have to use helium to cool it, actually. You could use liquid nitrogen to cool it, which would be really nice. Okay, so that's the story on, oh my God. Well, let's go on to something different. I have to put this away. I talk so much, it's terrible. But it's really interesting stuff. Okay, so nuclei. Let me just quickly jump to show you the demos. Let's see, is this thing working? Oh, we got 5 minutes. Well, very simply. One story is, well, the most important thing is that you know that I've already talked about the fact that nuclei were discovered, again, about 100 years ago, 1910, by Rutherford, by his experiments, where he shot, because, see, it goes back really to the beginning where you have radioactivity. Certain materials, uranium and others, shoot out particles, and they put the gold foil and saw the way the alpha particles were being scattered from the gold foil. What they did was have a screen here, and they counted how many particles came up to here, and so on. And in fact, they found some were coming straight back, which was quite amazing. And Rutherford explained it by saying that there was a massive center of the nucleus. And so you have to get the notation right. Z is the letter given to the atomic number. That's the number of protons. And in an ordinary atom, it's the number of electrons in the neutral atom. And it determines the chemistry, right? Now, it turned out that if you have all these protons in a proximity to each other in a very tight space, it turns out the whole deal is around 10 to the minus 15 meters across. And they're all packed here, and they're all positive. They're going to repel each other. So there has to be something else. And it turns out that around 1932, it was discovered that officially, although people must have suspected there's something else in there, that there are neutrons which act to sort of keep the protons apart and also have a force we call the nuclear force to hold the whole assembly together. And so you have a certain number of neutrons in a nucleus, and some of those, too, is we call the mass number, which is given the letter A. Now, a nuclide refers to just one of these species, and we have what's called isotopes, isotopes, and iso being the same, so they have the same Z. So it's the same chemistry, but different numbers of N is different. And those are interesting because they act the same, so they're chemically the same, but physically different. It's interesting here, the element gold has 32 isotopes, 32 different numbers of neutrons for its element one, I forget what gold is, but in any case, a lot of isotopes. Okay, let's look at how we see them. And I think we'll be doing some of this in the lab. Now, this is the familiar Geiger counter invented by Mr. Geiger, one of Rutherford's associates. And this, now I'm just counting particles coming in from space, basically. We're constantly being bombarded by particles coming from space, called cosmic rays, so we're never free. Going in an airplane is even worse, because there's less atmosphere to protect us from stuff coming in. That was a surprise, too. People thought that the only thing was radioactivity was radiation coming up from the Earth. But then somebody climbed the mountain and it got worse. So they realized that the particles are also coming in from outer space. But then we have all these different kinds of materials. This is a smoke detector. It has radioactive americium in it. Not too bad. Oh, sorry if you have to leave because we're about to have a party. And this is a radium dial. The old days they used to have radium dials because they would glow in the dark. Okay, so that's one way we look at them. By the click, what's happening is a charged particle is coming through and it's causing ionization. And when it's ionization, a little current flows and gives you a click. The other way, hopefully this thing is working. This is a cloud chamber. Well, I tell you what, let me move over to yet another. So as it happens, we have some fun thing here. We missed their birthdays by a little bit. The November 7th was the birthday of two very important nuclear scientists, Marie Curie and Lisa Meitner. I'll talk about them. And it happens that December 2nd is the anniversary of the first controlled nuclear chain reaction, 1942, done by Enrico Fermi. So this is Marie Curie. She was born in November 7th. She came to work in France. She married Monsieur Pierre Curie, her research advisor. And they had two daughters, Irene and Eve. Irene went on to win a Nobel Prize herself. But Pierre was killed in an accident. He was run over by a horse. That's pretty bad luck. But she carried on. And between them, she won a Nobel Prize with him in physics for work on radioactivity. And then she won a Nobel Prize in chemistry for discovering radium. So she won two Nobel Prizes in chemistry for radium and polonium. And then her daughter won a Nobel Prize in 1935. So before you leave, we should celebrate. I'm sorry, they should have done this sooner. We have some French cookies, and we have some for Lisa Meitner, some German cookies.